Hello, this is Miss Moore, and today during chemistry, we're going to discuss atoms and isotopes. Today's essential question: what is average atomic mass and how is it calculated? All right, let's start our discussion with atoms, and this is stuff you should already know. This is all hopefully review. All right, so atoms are made up of three types of subatomic particles: protons, neutrons, and electrons. And you should remember that the term subatomic particles, so protons, neutrons, and electrons are all below atomic particles. Protons have a positive charge and are found in the nucleus. Neutrons are also found in the nucleus and they have no charge. And then we have electrons, which have a negative charge, and they are found outside the nucleus in what we call the electron cloud. Because atoms are neutral meaning no charge. So because atoms are neutral, an atom will have the same number of protons and electrons. That's because protons have a positive charge, electrons have a negative charge, and positive and negative cancel out. So if we have the same number of protons or positive charges as electrons, negative charges, we'll end up with a neutral atom. The identity of an atom is determined by the number of protons it contains. Okay, so the identity of an atom is the number of protons. So if an atom has one proton, it's going to be hydrogen. If it has two protons, it will be helium. And if it has three protons, it'll be lithium, and so forth and so on. And we call the number of protons the atomic number. The atomic number can be found on the periodic table. It's usually up at the top, and it's a whole number, not a decimal. Okay, so again, the identity of an atom is determined by the number of protons it contains. This is known as the atomic number. The atomic number is also shown on the nuclear symbol. This thing right here is the nuclear symbol, and the atomic number is the bottom number. So calcium, just by looking at this without even looking at the periodic table, we know that calcium has 20 protons. Its atomic number is 20. The atomic mass of a single atom, and this is important, that we're talking about the atomic mass of a single atom, is the mass of the nucleus. And what subatomic particles are in the nucleus? Well, the protons and the neutrons. So the atomic mass of a single atom is the number of protons plus the number of neutrons. And the atomic mass is also found on the nuclear symbol, and it is the top number. So, all right, on to isotopes. What is an isotope? An isotope is an atom with the same number of protons but different number of neutrons, leading to a different mass. Okay, so remember that the identity of an atom is its number of protons. So for example, every lithium atom is going to have 3 protons, no matter what. However, every lithium atom may not have the same number of neutrons. So we could have a lithium atom that has atomic mass of 7, meaning it has 4 neutrons. We could have a lithium atom, let's get rid of the 7, with an atomic mass of 8, meaning it has 5 neutrons, and so forth. So this lithium, the 7,3Li lithium and the 8,3Li lithium are isotopes. They have the same number of protons, again, which makes them lithium, but in a different atomic mass, which means they have different number of neutrons. That's an isotope. Okay, one thing you may have noticed, or you should have noticed, is that the mass on the periodic table is a decimal. Okay, so for example, the mass of lithium on the periodic table is 6.94. And why is that? If mass is number of protons plus number of neutrons. Can't have a portion of a proton or a portion of the neutron, so where does this decimal number come from? Well, that has to do with average atomic mass. So the average atomic mass is the mass of the isotopes that compose an element weighted according to the natural abundance of each isotope. Okay, so the average atomic mass is not the actual mass of any one atom. Okay, it's the mass of, for my examples here, all of the lithium isotopes. And actually, we'd probably more likely have something like this, right? So it's the mass of all of those guys put together with their relative abundance. Like, for example, there are more lithium 7s than there are lithium 8s or 6s. Okay, so the average atomic mass is the mass of the isotopes that compose an element weighted according to its natural abundance of each isotope. And here's the formula. Average atomic mass equals the sum of the mass of each isotope times the mass of each isotope. That is not correct. Don't write that down. It's the mass of each isotope times the abundance of each isotope divided by 100. Okay, let's try a practice problem using that formula. And remember that average atomic mass equals sigma. That's this thing right here. I forgot to point out that this means sum. The sum of, so average atomic mass is the sum of the mass of each isotope multiplied by its abundance divided by 100. All right, so here's our practice problem. Copper has two naturally occurring isotopes. Copper 63, which has a mass of 62.9396 AMU, or atomic mass units, and it has a natural abundance of 69.17%, which means almost 70% of all copper is this copper 63. And then we have copper 65, which has an actual mass of 64.9278 AMU and a natural abundance of 30%. Calculate the atomic mass of copper, the average atomic mass. So we know that the average mass equals the sum of each of the isotopes, its mass times its abundance. So we're going to have, for copper 63, we have a mass of 62.9396 AMU times its abundance, which is 69.17%, plus the mass of copper 65, which is 64.9278 AMU, times its abundance, which is 30.83%, and this whole thing is divided by 100. All right, so putting that in our calculator, 62.9396 times 69.17, if I did this correctly, I get 4353.52, nope, 0.532132 plus 64.9278 times 30.83, and I got 2001.72. 4074. All of that is divided by 100. So now when we add those together, remember we're summing these, we get, I got 6355.256,208 divided by 100. And when we divide, giving us 63.55256, etc. And now, looking at sig figs, we have 6 and 4 and 6 and 4, so 4 sig figs. So, final answer is the average atomic mass of copper is 63.55 AMU. And if you look at your periodic table, you will note that the average atomic mass of copper is 63.55. Okay? Not too hard, I hope? Okay, let's switch gears a little bit and talk just a little bit about what happens to atoms when they interact. So what I really want to talk about here is percent composition. Okay, so the definition of percent composition is the percent by mass of each element present in a compound. So what in the world is a compound? That is 2 or more atoms that are bonded together. Okay, so for example, sodium chloride or water. Okay, those are examples of compound. So percent composition would be what percent of hydrogen, how much of the mass of water comes from the 2 hydrogen atoms, or how much of the mass of sodium chloride comes from the chloride ion. So that's what we mean by percent composition. Okay. So the formula for calculating percent composition is mass percent of an element is the total mass of the element in the compound divided by the total mass of the compound multiplied by 100. So let's try this real quick. What is the mass percent of hydrogen in water? So water is H2O, and it's made up of 2 hydrogens and 1 oxygen. So the mass of hydrogen is 1.008, but there are 2 of them, giving us a total mass of hydrogen of 2.016. And the mass of oxygen, I guess I should write this here, hydrogen, oxygen is 16.00, and there's 1 of them. So the total mass of H2O is 18.016. We're adding, remember we added together this, well, not that one. Let's try that again. We added together this and this, right, to get this. So we look at sig figs. When you're adding, you look at the decimal points. So we're going to end up with 18.02. Okay, so now to figure out the percent hydrogen, we take the total mass of hydrogen, which was 2.016, divided by the mass of the whole compound, in this case is 18.02. Multiply that by 100, and that gives us a percent of let's see, how many sig figs here? 4 sig figs. So 11 point, well, let me write out a larger number. We'll practice sig figs. 1, 8, 7, 5, 6, etc. We have here 2 sig figs and, no, why did I say 2? Sorry. 4 sig figs and 5 sig figs. So our final answer is going to be these here. So the percent hydrogen in water is 11.19%. Okay, so that is how you figure out the mass percent of an element in the total compound, which should mean, remember that the mass should be out of 100%, right? So we could actually figure out the percent of oxygen by subtracting 11.19 by 100 to give us the percent of mass of oxygen. And the last topic for today is the law of definite proportions. So the law of definite proportions says that different samples of the same compound always contain the elements it's made from in the same proportion by mass. So if we had, what that's trying to say is that if we had 1 liter of water, 11.19% of that would be hydrogen. If we had 100 liters of water, 11.19% of that would be hydrogen. So no matter where we get our sample, in water, 11.19% of that is always hydrogen. That's what we mean by the law of definite proportions. So the last step for today is to try using the law of definite proportions. All right, let's try a couple practice problems here. So we have 2 samples of carbon dioxide, and they're decomposed into their constituent elements, meaning carbon and oxygen. So let's see. We've got 1 sample producing 25 grams of oxygen and 25.6 grams of oxygen and 9.6 grams of carbon. Okay. The second sample produced 21.6 grams of oxygen and 8.1 grams of carbon. Shows that these results are consistent with the law of definite proportions. Now, there's a lot of ways we could go about solving this problem, but what I'm going to do is calculate the mass percent of one of these, either the oxygen or the carbon, and we'll do the oxygen since it's written first. Law of definite proportions says that the percentage should be the same. So percent, try this with yellow. So the percent of oxygen in the first sample, so let's see, we have 25.6 grams divided by, now we need to add up the total mass, right? So it's going to be the mass of the oxygen plus the mass of the carbon. And that gives us 35.2 grams. Multiply that by 100. 3 sig figs when we do the calculations. If I did this correctly, I got 72.7% oxygen. Let's do this again for the second sample. So percent oxygen in the second sample. Let's see, we start with 21.6 grams of oxygen, and this time the total mass, we're going to add up 21.6 oxygen and 8.1 carbon, giving us 29.7 grams. Multiply that by 100, and that gives us, and I forgot to write 100 on that one above, that's sort of weird, there you go. That gives us, again, 72.7%. So these results are indeed consistent with the law of definite proportions because we have the same proportion of oxygen, even though the sample is different and the total mass of the sample was different. They're still combining in the same proportions. Okay, so let's try one more practice problem. What mass of oxygen could be produced from 89.1 gram sample of carbon dioxide? So we know, a little bit more tricky, right? We know the total mass of the compound, it's 89.1 grams. So we know that. What we're trying to find is the mass of oxygen, which would be this here. That's not going to be enough for us. But we also know from the law of definite proportions that the proportions should stay the same. And we just solved and found out the percent oxygen is 72.7%. Right? So 72.7. There. Now we can calculate the mass of oxygen. So let's do a little rearranging here. Let's get X by itself. So we'll have X equals 72.7 times 89.1 divided by 100. So let's check that out. And when I calculated that, I came up with 64 with the right number of sig figs, 8. I actually got 64.7757, but 64.8 grams of oxygen. Okay, so the law of definite proportions can be kind of handy because if we know what the proportions should be, the percent carbon and the percent oxygen, and we know the mass of our sample, we can figure out the mass of each of the constituent elements or the things that it's made up of. Okay, that's it for today. Have a good one.